On November 15th, 2025, something extraordinary happened in the world of astronomy. For the first time, a bright, compact object, officially named 3IATLAS, or C/2025N1, was captured on video by multiple observatories, sparking a deep sense of curiosity and confusion among scientists. This object, which is moving through space at incredible speed, is officially classified as an interstellar visitor. It's traveling on a hyperbolic trajectory, meaning it is not bound to our solar system and will eventually escape into the depths of space. Its closest approach to Earth is set for December 19th, 2025, but the mystery surrounding it deepens as astronomers struggle to understand what they are observing. A key characteristic of comets, which we would expect from a celestial object like 3I-ATLAS, is a visible coma. This glowing halo of gas and dust forms when the sun's heat causes the icy nucleus of the comet to sublimate, releasing material into space. But 3I-ATLAS defies this typical behavior. When captured on film, it appears as a small, bright, compact point of light, sharp and star-like in its intensity. In other words, it lacks the expected coma that would make it appear fuzzy or diffuse. This striking difference between this video and previous comet observations is what has captured the attention of the global scientific community. Even more puzzling are earlier reports from professional observatories which claimed that 3I-ATLAS was generating multiple jets, streams of material shooting out from the object's surface. Some of these jets even appeared to form anti-tails, which are jets that seem to point toward the sun rather than away from it. Yet these jets should create a large visible envelope of gas around the object. But in the footage captured by amateur astrophotographers, this diffuse cloud is mysteriously absent. How can an object with visible jets appear to be so bare and compact in images? Astronomer Avi Low is calling for transparency, demanding that NASA release high-resolution images taken from Mars' orbit by the Mars Reconnaissance Orbiter. He argues that science should never be held up by bureaucratic delays. These images, taken more than a month ago, could hold the key to understanding what 3I-ATLAS actually is, and Low's frustration is palpable as he urges for their release. This issue raises more than a few eyebrows. Comets are not only defined by their visual appearance, but also by their behavior. The apparent lack of a coma in the case of 3I-ATLAS challenges our very understanding of how comets function as they approach the sun. What's truly perplexing is that this object was initially identified as a comet, a classification based on its trajectory, which confirmed its interstellar origin. But if it behaves so differently from typical comets, is it really just an unusually active comet, or could it be something else entirely? The speed at which 3I-ATLAS is traveling only adds to the complexity of the situation.
Its velocity, far greater than that of anything native to our solar system, marks it as a visitor from interstellar space. This object, once thought to be a mere curiosity, has now become a critical subject of study. With its closest approach to Earth rapidly approaching, astronomers know they have a limited window to study it before it races off into the unknown void. The initial video footage of 3I-ATLAS ignited widespread curiosity across astronomy forums and among amateur astrophotographers worldwide. Within hours, thousands of eyes had scrutinized the same image, and the consensus was clear. This object was unlike any comet they had ever observed. Despite its bright, sharp appearance, it didn't show the characteristic features of a comet, which led to confusion among even the most seasoned astronomers. Typically, comets, especially those approaching the sun, display a coma, a halo of gas and dust created as their icy cores sublimate due to solar radiation. This visible coma is what makes comets so recognizable. However, in the footage captured by Chuck's astrophotography operation based in the United States, 3IATLAS appeared naked, devoid of this expected gaseous envelope. Instead, it looked like a pinpoint of light, almost like a star. This striking difference raises an important question. Is this truly a comet, or are we seeing something else, something entirely unexpected? To add to the mystery, professional observatories had already reported that 3IATLAS was generating at least 7 distinct jets. These jets were streams of gas and dust shooting out in various directions. Some even created anti-tails, an optical illusion where the material appears to point toward the sun rather than away from it. Normally, these jets would form a diffuse cloud around the object, creating the familiar coma. Yet the absence of this visual cloud in amateur footage only deepens the confusion. At first, some speculated that the geometry of the situation was playing tricks on the observers. Perhaps the tail of the object was pointing directly away from Earth, which would make it appear shorter or invisible due to perspective. Or maybe the coma was there, but too faint to register in short-exposure photos. But even after considering these possibilities, something didn't add up. The object's behavior seemed to diverge from what scientists knew about comets, especially interstellar ones. The absence of the coma, combined with the unusual nature of the jets, called for a re-examination of the object's classification. The trajectory of 3IATLAS only compounds the mystery. This interstellar object, confirmed to be on a hyperbolic path, is not bound by the sun's gravity, and it will eventually escape into deep space. However, unlike anything native to our solar system, its speed is far greater than what we would expect from a typical comet.
This astronomical visitor is hurtling through our solar system at speeds that defy the typical velocities of objects orbiting the Sun. Its closest approach to Earth is set for December 19, 2025, and the scientific community knows that this is their best and perhaps only chance to gather definitive data before it moves out of reach. Astronomers have long observed comets, and they know what to expect. A comet should have a fuzzy, diffuse appearance when it's close to the Sun. Even faint comets, distant ones, exhibit this fuzzy halo when observed from Earth. However, 3IATLAS continues to defy this expectation. In multiple amateur frames taken across the globe, the object appears as a bright, sharp point of light, like a star, without any visible coma or tail. Yet professional telescopes, such as those operated by the Virtual Telescope Project in Italy and the Hubble Space Telescope, have reported seeing faint, characteristic features like a coma and tail. This discrepancy between professional and amateur observations raises questions about the nature of 3IATLAS. What are the key differences in the equipment and techniques used by professionals compared to amateurs? Why does the object appear so differently in the images taken by professionals? The answer lies partly in the equipment used and the technical differences in how data is collected and processed. Professional observatories are equipped with large telescopes with long exposure times, which allow them to capture faint features. These telescopes use narrowband filters to isolate specific wavelengths of light, such as emission lines from specific elements like oxygen or carbon. These filters help reveal jets, outgassing, and other faint features that would be invisible in broad-spectrum imaging. In contrast, amateur astronomers typically use smaller telescopes and shorter exposure times. As a result, when observing an object like 3IATLAS, they often capture a point of light without the extended features. If the coma is faint, it could be entirely invisible in these short exposures. Additionally, many amateur astronomers use standard RGB filters, which do not discriminate between different wavelengths of light. This lack of specificity could explain why amateurs are not seeing the coma that professionals report. However, even with these technical differences, some amateur observers are stacking multiple frames to boost the signal and still seeing the same compact, star-like point of light.
As the mystery of 3IATLAS continues to unfold, one prominent scientist is pushing for transparency. Avi Loeb, a physicist from Harvard University, is demanding that NASA release high-resolution images of 3I-ATLAS taken by the Mars Reconnaissance Orbiter. The high-rise camera aboard the orbiter captured these images during the object's close pass by Mars in October of 2025. With its superior resolution, the high-rise camera could reveal crucial details about the object that ground-based telescopes simply cannot capture due to atmospheric distortion. Despite the significance of this data, as of November of 2025, NASA has yet to release the images. Loeb's frustration is clear, and he has publicly criticized the delay, arguing that scientific discoveries should not be delayed by bureaucratic processes. This call for transparency highlights the urgent need to understand 3I-ATLAS before it moves beyond our observational reach. If there is something unusual about the object's structure or composition, these images might provide the key to understanding it. But why is NASA withholding these images? There are a few plausible explanations. Data from high-resolution instruments like HiRISE require significant processing time, as raw images must be calibrated and corrected for various factors. Additionally, there is a standard protocol that grants exclusive access to the research team for a certain period before the data is made public. However, given the time-sensitive nature of this object, scientists and enthusiasts alike are eager for the release of this data to help answer the growing questions surrounding 3I-ATLAS. As the object known as 3I-ATLAS continues its journey through our solar system, its orbital characteristics raise intriguing questions. The path it's following is hyperbolic, meaning it is not bound to our sun's gravity, and it will eventually leave our solar system for good. However, the crucial moment for astronomers is not just the object's arrival in our neighborhood, but rather the date when it will come closest to Earth, December 19, 2025. Understanding the orbital context is vital because it will allow scientists to better interpret the observations made during this time. On December 19th, 3I-ATLAS will be approximately 1.88 astronomical units, about 270 million kilometers from Earth. While this is still a significant distance, it is close enough for large telescopes to obtain their best resolution, offering the clearest and most detailed view of the object. The closer it comes, the more photons it will emit, allowing us to observe it with sharper clarity. This date is also essential because of the angle at which Earth-based telescopes will be able to observe the object. As it approaches Earth, 3I-ATLAS will rise higher in the pre-dawn sky, making it more visible to observers in the Northern Hemisphere.
This is a critical opportunity, as it allows scientists to capture images without the interference of the sun's glare, which would otherwise distort observations. For amateur astronomers, December 19th represents the sweet spot for observing 3I-ATLAS. According to magnitude estimates, the object will likely be around magnitude 11.5 at its peak, meaning it will not be visible to the naked eye, but will still be observable with telescopes of at least 6 inches in aperture. With the right equipment and ideal sky conditions, both professional and amateur astronomers will have their best chance to capture the data needed to confirm whether 3I-ATLAS is indeed a comet, or if it is something far stranger. This is the most optimal time for observational campaigns, and it may represent the last opportunity to uncover the true nature of 3I-ATLAS before it moves farther away, fading into the void of space. If there are any anomalous features, such as fragmentation, jets that behave unusually, or unexpected geometric structures, they will most likely appear during this period. Once the object begins its journey away from the sun, it will start to dim, making it harder to observe. By January 2026, it will likely be too faint for most amateur telescopes to capture, and by February, it will require dedicated professional equipment. This narrowing window of opportunity makes December 19th not just another day, but the pivotal moment when astronomers will either confirm that 3I-ATLAS is a strange but natural comet, or reveal something truly unprecedented.
As the debate surrounding the nature of 3I-ATLAS continues, astronomers are faced with several competing hypotheses that offer different explanations for its strange behavior. These hypotheses are grounded in the data that has been collected thus far, but none has been definitively proven. The data gathered during the critical period in December will help refine or reject these hypotheses. The first hypothesis suggests that 3I-ATLAS is an unusual natural comet. According to this theory, the object formed in another star system was ejected into interstellar space and is now passing through our solar system for the first and only time. The absence of the coma in amateur images could be explained by the geometry of the object's trajectory, with the coma being too faint to detect from our vantage point. Additionally, the high carbon dioxide to water ratio observed in the object's composition might reflect the formation conditions in a colder environment than our solar system, where carbon dioxide was more prevalent. This hypothesis would be supported if further observations confirm that the object is exhibiting natural comet behavior, such as fragmentation or sublimation under solar heating. The second hypothesis narrows the natural explanation even further, proposing that 3I-ATLAS is a fragile, fragmenting rubble pile.
In this scenario, the object would not be a solid nucleus, but rather a loose collection of smaller fragments held together by weak gravity. This would explain the complex jet morphology and the 7 distinct jets observed in earlier reports. If the object were to fragment under the stress of solar radiation, it could create multiple outbursts that would mimic the behavior of a comet, but with more chaotic dynamics. If further observations show signs of fragmentation, such as changes in brightness or jet configuration, this hypothesis would gain support. The third hypothesis, which remains controversial, is that 3I-ATLAS is an artificial object, either a probe, spacecraft, or a piece of defunct technology from another civilization. Proponents of this idea point to the absence of a coma, the compact appearance, and the jets as evidence of artificial propulsion systems rather than natural outgassing. If 3I-ATLAS were truly an engineered object, the jets might not be caused by sublimating ice, but by some kind of exhaust from an internal system. Extraordinary claims, however, require extraordinary evidence. For this hypothesis to be supported, scientists would need to detect artificial materials or technologies, such as metals, alloys, or even signals that are consistent with technological propulsion. The fourth and final hypothesis suggests that the anomaly is a result of observational or processing artifacts. In this view, the missing coma in amateur frames could be explained by technical limitations, such as short exposures or inadequate stacking. According to this theory, the object is still a natural comet, and the apparent anomalies in the data are simply due to imperfect observational techniques. As December 19th approaches, the scientific community will have to carefully analyze the incoming data to test these hypotheses. Every observation, from jet morphology to spectral analysis, will provide valuable clues that could either confirm or debunk these competing theories. The mystery of 3I-ATLAS has captivated both professional astronomers and the public, and the resolution of this mystery could reshape our understanding of interstellar objects for years to come. One of the key features that sets 3I-ATLAS apart from typical comets is its behavior in space, specifically its acceleration. As comets travel through the solar system, they experience a phenomenon known as non-gravitational acceleration. This is caused by the sublimation of gases from the comet's surface, which creates jets of material that push the object slightly off its expected trajectory. While this effect is generally subtle, it plays an important role in defining the comet's path. In the case of 3I-ATLAS, the data suggests that the non-gravitational acceleration is significant. Swift UV observations indicate a mass loss rate of about 40 kilograms per second at a heliocentric distance of 3.51 astronomical units.
For context, typical short-period comets might lose just a few kilograms per second at that distance, making the rate observed in 3I-ATLAS quite remarkable. This suggests that the object is outgassing at a much higher rate than other comets. To understand how this mass loss translates into acceleration, let's do the math. With 40 kilograms of material being ejected every second,
and assuming typical ejection velocities of 500 to 1,000 meters per second, the resulting thrust is around 20 to 40 newtons. While this may seem small, equivalent to the weight of a gallon of milk on Earth, it can have a significant effect over time. If this force is applied continuously for 100 days, it would cause a change in velocity of approximately 10 meters per second, which is detectable and measurable by astronomers. The direction of this thrust is also crucial. If the force is directed primarily away from the Sun, then it suggests that the outgassing is occurring on the day side of the comet, which is what we would expect. However, if the thrust is pointing in a direction that doesn't align with solar heating or the expected behavior of a comet, then that could be a sign of something unusual, perhaps even something artificial. In the case of 3I/ATLAS, the non-gravitational acceleration appears to match the outgassing observed, with the direction and magnitude of the thrust aligning with the jet's morphology. This is consistent with natural comet behavior, but there is still a possibility that something more complex is at play, especially when considering the unusual chemical composition of the object. Spectroscopy, the study of light and its interaction with matter, has provided astronomers with a wealth of information about 3I/ATLAS. By analyzing the light emitted by the object and comparing it to known emission lines from different molecules, scientists have been able to identify the chemical composition of the comet's coma and jets. The most notable discovery from the James Webb Space Telescope, or JWST, is the unusually high carbon dioxide to water ratio in the object's composition, which is roughly 8 to 1. This ratio is extremely high compared to typical comets in our solar system, where the carbon dioxide to water ratio generally ranges from 0.01 to 0.5. A ratio of 8 means that carbon dioxide overwhelmingly dominates the composition of 3I/ATLAS's outgassing, while water vapor is present in much smaller amounts. This finding suggests that 3I/ATLAS may have formed in a much colder environment than our solar system, or it may be an older object that has undergone significant chemical transformation over billions of years. One possible explanation for this unusual chemistry comes from the effects of cosmic ray processing. Over time, these rays can break chemical bonds in the object's icy surface, transforming carbon monoxide into carbon dioxide and eroding the water ice. This process could account for the high carbon dioxide to water ratio observed in the object's outgassing. Additionally, polarization measurements of light reflected off 3I/ATLAS have revealed an extreme negative polarization branch, a feature not commonly seen in comets. Polarization measures the way light waves oscillate in different directions, and natural surfaces, such as dust or ice particles, scatter light in characteristic patterns. The extreme polarization observed in 3I/ATLAS suggests that the surface or particles of the coma might have unusual optical properties. Perhaps they are larger or more irregularly shaped than typical comet dust, or the surface may have a different texture, such as being more porous or reflective. While these findings are certainly intriguing, they are not definitive proof of anything extraordinary. The high carbon dioxide ratio could simply be a result of the object's age and exposure to cosmic rays, and the extreme polarization may be a natural but rare characteristic of interstellar comets. However, these anomalies continue to fuel speculation that 3I/ATLAS is unlike any comet we've observed before. Before 3I/ATLAS, only two other confirmed interstellar objects had passed through our solar system: Oumuamua, discovered in 2017, and Borisov, discovered in 2019. Each of these objects presented their own mysteries and challenges to our understanding of interstellar bodies, and each defied traditional expectations in different ways. Oumuamua was an elongated object, possibly cigar-shaped, that showed no signs of outgassing. It had no visible coma or tail,
and its trajectory was slightly deviating from a pure gravitational orbit, which led some scientists, including Avi Loeb, to speculate that it might be an artificial object, perhaps a light sail or a probe sent from another civilization. While most astronomers rejected this hypothesis, Oumuamua's unusual behavior raised important questions about what interstellar objects could be. In contrast, Borisov, which was discovered just 2 years later, behaved like a typical comet. It had a visible coma, a tail, and the expected outgassing patterns. Its composition was consistent with that of comets from our solar system, and its trajectory showed no signs of deviation from standard cometary behavior. Borisov provided a more reassuring example of what interstellar comets might look like, confirming that some interstellar objects could indeed follow familiar patterns. Now, with 3IATLAS, we are confronted with something that doesn't neatly fit into either category. It exhibits signs of outgassing, but its compact appearance and unusual chemical composition make it more complex than Borisov.
The absence of the coma in amateur images and the extreme polarization are features that distinguish it from the standard comet model. But the object's trajectory and some of its outgassing behaviors suggest that it is still fundamentally a comet. In many ways, 3IATLAS represents a new class of interstellar visitors, one that challenges our assumptions about how objects from other star systems behave. While it shares some characteristics with other comets, its anomalies suggest that we are dealing with something far more unusual. Whether 3IATLAS is a natural comet, a fragmenting rubble pile, or an artificial object remains to be seen, but its passage through our solar system offers a rare and invaluable opportunity to learn more about the diverse range of objects that populate the galaxy. In today's world, the rapid spread of information via social media has significantly changed how scientific discoveries are shared and discussed. In the case of 3IATLAS, the role of amateur astronomers and the viral nature of social media have created a unique environment where scientific inquiry is constantly in the public eye. Images of 3IATLAS, taken by amateur astrophotographers, spread quickly across platforms like Reddit, Twitter, and YouTube. Within hours, people were discussing the object, speculating about its origin, and drawing conclusions about its true nature. While the involvement of amateur astronomers is invaluable, providing diverse data points and real-time coverage, this sudden influx of information also presents challenges for scientists. The immediacy of social media can amplify misinformation and sensationalism, as people often jump to conclusions before professional analysis can take place. When an amateur image captures a seemingly bizarre feature, such as the missing coma, it's easy for speculation to spiral into claims that 3IATLAS is an alien spacecraft or something even more extraordinary. This tension between public curiosity and scientific rigor is not new, but it has become much more pronounced in the digital age. In the past, scientific discoveries would go through a careful process of peer review before they were shared with the public. Now, images, videos, and even preliminary conclusions can be broadcast in an instant, leaving scientists to play catch-up. This fast-paced flow of information puts pressure on the scientific community to release findings quickly, even when the data is still being analyzed and verified. As the hype surrounding 3IATLAS grows, so too does the pressure on scientists to provide clear answers. However, the complexities of astronomical research mean that definitive answers take time. The process of gathering data, analyzing it, and reaching conclusions is slow and deliberate. But in the age of social media, where sensational headlines attract more attention than careful, nuanced science, there's a constant push to make bold claims.
The temptation to speculate is high, especially when the public is eagerly waiting for answers. This dynamic complicates the scientific process, as media and public excitement sometimes outpace the data. Solar weather, often considered a background concern in astronomy, plays a crucial role in the quality of observations made by both amateur and professional astronomers.
The most recent solar flare, which took place on November 11-12, 2025, is a perfect example of how solar activity can interfere with scientific observations. The flare, categorized as an X5.1 class event, was one of the strongest solar flares of the year. It emitted a burst of radiation that affected radio waves, GPS systems, and satellite operations, and also interfered with radio telescope observations. The flare also had an impact on the study of 3IATLAS. Radio telescopes, such as the South African-based Meerkat array, had been monitoring the object for hydroxyl emissions, a common indicator of water vapor. However, solar flares can overwhelm radio telescopes by flooding the radio spectrum with noise, making it difficult to detect faint signals. If a significant event, like a jet outburst or a fragmentation event, occurred during the flare, it could have been missed by radio observatories. Optical telescopes, on the other hand, may have caught the event, but the absence of complementary radio data would leave a gap in the interpretation. Additionally, solar flares can affect the ionosphere, the layer of the Earth's atmosphere that refracts radio waves. When charged particles from the sun interact with the ionosphere, they can distort radio signals, further complicating observations of distant objects like 3IATLAS. This is a reminder that our observations of space are not isolated from the environment around us. The sun's activity can interfere with the instruments we rely on to study objects like 3IATLAS, and as a result, astronomers must carefully account for these factors when interpreting data. The study of objects like 3IATLAS is on the cusp of a technological revolution, thanks to advancements in quantum computing. These computers, which operate on the principles of quantum mechanics, are poised to solve complex problems that traditional computers cannot. For instance, modeling the chaotic dynamics of cometary outgassing, jet formation, and the interactions of gas and dust particles in three-dimensional space is a computationally intensive task. Classical computers can approximate these systems, but they struggle when the complexity becomes nonlinear and multidimensional. Helios, a groundbreaking quantum computing system, has recently reached a major milestone by simulating highly complex systems with unprecedented precision. Unlike traditional computers which approximate solutions, quantum computers can solve problems in their native form, accounting for all the intricacies of the interactions between particles.
By using Helios to simulate the outgassing, jet dynamics, and dust interactions of 3IATLAS, scientists could gain insights into the object's behavior that were previously unattainable. For example, researchers could input observational data from 3IATLAS into a quantum model and simulate numerous scenarios to compare predicted cometary behaviors with the actual data. The ability to model the object's behavior with such high precision could reveal whether 3IATLAS is behaving like a typical comet or if it is displaying some anomalous features that challenge our understanding of comets. Although quantum computing won't provide a definitive answer on its own, it can help flag inconsistencies in the current models and push the boundaries of what we know about interstellar objects. In addition to artificial intelligence, AI is becoming an increasingly important tool in astrophysical research. AI algorithms are capable of processing vast amounts of data, identifying patterns and making predictions that would be difficult for human researchers to uncover on their own. For example, AI could be used to analyze light curves, jet orientations, spectral ratios, and acceleration vectors from both amateur and professional observations of 3IATLAS. By feeding this data into AI systems, researchers can construct potential physical models of the object, test these models against the observed data, and identify any anomalies or unexpected patterns. If the data reveals strange behavior, such as non-gravitational acceleration that doesn't match the expected patterns of outgassing, AI could highlight these discrepancies and prompt further investigation. This approach allows scientists to test natural versus engineered models, potentially uncovering hidden forces at play in the dynamics of 3IATLAS. While AI models are not infallible, they can greatly expedite the process of analyzing large data sets and prioritizing anomalies for further study.
As our observational tools improve, AI will become an essential companion in the search for understanding the universe's most mysterious objects. The study of interstellar objects like 3IATLAS is evolving rapidly, thanks to the remarkable advancements in astronomical technology. One of the most significant developments in recent years has been the launch of the James Webb Space Telescope, WAST, which has already made groundbreaking strides in exoplanet research and is now poised to play a crucial role in studying interstellar visitors. WAST's capabilities go beyond those of previous space telescopes. With its infrared instruments, WAST can detect wavelengths of light that are invisible to optical telescopes like Hubble, allowing it to observe distant objects with unprecedented clarity. For example, WAST has already demonstrated its ability to map the atmosphere of an exoplanet, revealing temperature variations, chemical composition, and structural features that would otherwise remain hidden.
These same techniques could be applied to 3IATLAS. By using JWST to observe the object in infrared wavelengths, scientists can analyze the chemical composition of its coma, jets, and nucleus with a level of detail that was previously unimaginable. JWST's sensitivity to faint signals could reveal subtle features of 3IATLAS's outgassing and structural integrity, potentially answering some of the lingering questions about its behavior and composition. Moreover, JWST's ability to observe objects in real time and in multiple wavelengths could offer a more complete understanding of the object's dynamics. By combining infrared data with optical and radio observations, astronomers can build a three-dimensional picture of the object's structure, its outgassing behavior, and its interaction with solar radiation. This comprehensive approach could provide the final piece of the puzzle and help confirm whether 3IATLAS is simply an unusually active comet or something entirely different. As December 19th approaches, the scientific community is preparing for what may be the most critical observations of 3IATLAS. The object is rapidly approaching its closest point to Earth, and astronomers around the world are preparing to capture the data needed to understand its true nature. This is a rare opportunity, as most interstellar objects pass through our solar system without giving us enough time to observe them in detail. The mystery of 3IATLAS is not just about one object. It represents a broader challenge in astronomy. As we continue to explore the universe and encounter more interstellar visitors, we must be prepared to confront the unexpected. 3IATLAS has already shown us that not all objects from other star systems behave according to our existing models. Whether it's the unusual absence of a coma in amateur images or the extreme chemical composition, this object is pushing the boundaries of what we know about comets and interstellar objects. The research surrounding 3IATLAS also highlights the importance of collaboration in science. Astronomers, both professional and amateur, are working together to gather as much data as possible. Observatories around the world are coordinating their efforts, and new technologies like quantum computing and AI are helping to accelerate the analysis. This spirit of cooperation and innovation is crucial as we continue to unlock the mysteries of the cosmos. As the data from December's observations begins to pour in, we will finally have answers to some of the most pressing questions about 3IATLAS. Is it a strange but natural comet? Is it a fragmenting rubble pile? Or is it something entirely different, perhaps even artificial? The answer may lie in the details of its jets, its chemical composition, or its non-gravitational acceleration.
But one thing is certain. The mystery of 3IATLAS has already expanded our understanding of the universe, and the search for answers will continue long after the object has passed us by. The study of interstellar objects like 3IATLAS is not just about understanding one strange visitor to our solar system. It also holds broader implications for the future of space exploration and our understanding of the universe. These objects offer us a unique glimpse into the conditions and processes that occur in other star systems,
providing a valuable opportunity to study the diversity of celestial bodies beyond our own solar system. One of the key lessons we've learned from 3IATLAS is that interstellar objects can behave in ways that are not easily explained by traditional models. The object's unusual chemistry, its apparent lack of a coma, and its rapid movement all challenge our assumptions about what comets and other objects from other star systems should look like. As we encounter more interstellar visitors in the future, it's likely that we'll continue to see more surprises that force us to rethink our understanding of the cosmos. The data gathered from 3IATLAS will also help refine our models of cometary behavior, potentially leading to new insights into the formation and evolution of comets and other small bodies in the solar system. By comparing 3IATLAS to previous interstellar objects like Oumuamua and Borisov, astronomers will be able to build a more comprehensive picture of the diversity of objects in the galaxy. Moreover, the study of 3IATLAS serves as a reminder of the importance of scientific curiosity and perseverance. While the object may eventually fade into the background of space, the data collected will continue to shape our understanding of the universe for years to come. It's a testament to the power of observation, analysis, and collaboration, and it underscores the fact that even the most unexpected discoveries can lead to profound insights into the nature of the cosmos. As we move closer to December 19, 2025, the excitement surrounding 3IATLAS will only intensify. The critical observations made during this period will provide the answers we've been waiting for, and they will help determine whether 3IATLAS is an unusually active comet or something far more mysterious. Whether it's a natural phenomenon or an artificial object, the answers we uncover will have profound implications for our understanding of the universe and our place within it. In the end, the mystery of 3IATLAS is not just about one interstellar object. It's about pushing the boundaries of science, embracing the unknown, and continuing to explore the vast expanse of space. As we prepare for the next chapter in this exciting story, we can only hope that the answers we find will inspire future generations of scientists to look up at the stars and ask the questions that have yet to be answered.
The study of objects like 3IATLAS has entered an era of unprecedented technological advancement thanks to the launch of the James Webb Space Telescope, or JWST. This revolutionary observatory, which has already made groundbreaking contributions to the field of exoplanet research, is now positioned to provide critical insights into the nature of interstellar visitors like 3IATLAS. JWST's capabilities far exceed those of previous space telescopes, and its infrared instruments are set to transform our ability to observe distant celestial bodies with unprecedented precision. Unlike its predecessors, JWST can observe objects in the infrared spectrum, capturing wavelengths of light that are invisible to optical telescopes like Hubble. This is particularly important for studying objects like comets and asteroids, whose faint emissions often lie in the infrared range. For example, JWST has already demonstrated its ability to map the atmosphere of exoplanet WASP-18b, revealing intricate details about the planet's composition, temperature, and structure. This achievement has opened up new avenues for understanding the conditions on distant worlds, and now JWST is poised to apply its powerful instruments to study 3IATLAS in a similar fashion. Using JWST, astronomers will be able to analyze the chemical composition of 3IATLAS's coma, jets, and nucleus with exceptional clarity. The telescope's sensitivity to faint signals could provide unprecedented insight into the object's outgassing behavior and the structure of its surface.
By studying the infrared light emitted by 3I-ATLAS, scientists can learn more about its volatile composition, potentially revealing crucial clues about where and how it formed in its distant star system. Additionally, JWST's ability to capture data across multiple wavelengths will allow astronomers to gain a comprehensive understanding of the object's behavior. By combining infrared observations with those from optical and radio telescopes, they will be able to construct a detailed three-dimensional picture of 3I-ATLAS. This approach will offer a deeper understanding of how the object is interacting with solar radiation, its internal structure, and the dynamics of its outgassing. Such multi-wavelength observations are key to answering lingering questions about the object's origin, nature, and behavior. For 3I-ATLAS, JWST's unprecedented observational capabilities could provide the answers that have eluded astronomers thus far. By observing this object in the infrared, JWST has the potential to uncover hidden features that might not be visible in optical wavelengths, bringing us closer to solving the mystery of whether this interstellar visitor is a natural comet, an artificial object, or something else entirely. If successful, this will represent a groundbreaking achievement in the study of interstellar objects. As December 19th approaches, the excitement surrounding 3I-ATLAS reaches new heights.
This is the date when the object will be closest to Earth, and astronomers around the world are preparing to observe it with their most powerful telescopes. The window of opportunity to study 3I-ATLAS is rapidly closing, and the data collected during this critical time will determine the object's true nature. Astronomers have long been fascinated by interstellar objects, but 3I-ATLAS presents a unique set of challenges. Unlike previous interstellar visitors like Oumuamua and Borisov, which exhibited relatively typical cometary behavior, 3I-ATLAS is displaying several anomalies that have caused scientists to question their assumptions about what comets and other celestial objects can do. The absence of a coma in amateur images, the object's unique chemical composition, and its high velocity all raise intriguing questions about whether 3I-ATLAS is simply a highly active comet or something far more extraordinary. In the weeks leading up to the critical December 19th observation window, astronomers will have the chance to gather vital data that could confirm or disprove these hypotheses. The object's behavior in the sky, its trajectory, and the patterns of its outgassing and jet emissions will provide key clues. For instance, if 3I-ATLAS continues to display the same unusual features, such as the compact appearance in amateur images, it could suggest that the object is behaving in ways that are not typical for comets. On the other hand, if the object behaves more like a traditional comet in the coming weeks, the mystery will likely resolve itself, and scientists will confirm that 3I-ATLAS is a natural comet after all. Regardless of the outcome, the data collected during this period will be invaluable for understanding interstellar objects in general. This will not only help scientists classify 3I-ATLAS, but will also contribute to the broader study of comets, asteroids, and other celestial bodies that pass through our solar system. The observations made in December will provide insights into the conditions and processes that occur in other star systems, and they could reveal new information about the diversity of objects in the galaxy. The study of interstellar objects like 3I-ATLAS is not just about understanding one strange visitor to our solar system. It holds broader implications for space exploration and the study of the cosmos. As more interstellar objects pass through our solar system, we have the unique opportunity to study these visitors in detail, gaining insights into the conditions and processes that occur in distant star systems. Interstellar objects are not all alike. They come from different parts of the galaxy, formed under different conditions, and subjected to different cosmic forces. By studying 3I-ATLAS and other interstellar visitors, we can learn more about the diversity of celestial bodies beyond our solar system.
For example, the high carbon dioxide to water ratio observed in 3I-ATLAS could suggest that it formed in a colder environment than our solar system, where carbon dioxide was more prevalent. On the other hand, the object's high velocity and its unusual outgassing patterns suggest that it may have experienced unique conditions during its journey through space. The data gathered from 3IATLAS will also help refine our models of cometary behavior. While many comets in our solar system exhibit similar features, the anomalies observed in 3IATLAS challenge the assumptions that have been built into our understanding of comets. If 3IATLAS is confirmed to be a natural comet, albeit an unusual one, it will expand our knowledge of the range of behaviors that comets can exhibit. However, if it is found to be something entirely different, perhaps an artificial object or a fragmenting rubble pile, then our understanding of interstellar objects will need to be revised once again. The broader lesson from the study of 3IATLAS is that the universe is full of surprises, and the more we explore, the more we learn about the diversity of celestial bodies that populate it. Whether 3IATLAS is a strange but natural comet or something entirely different, its passage through our solar system represents a unique opportunity to push the boundaries of human knowledge and understanding. It is a reminder that the study of space is never static, and every new discovery opens the door to more questions and possibilities. In the digital age, social media has drastically altered the landscape of scientific discovery. The rapid dissemination of information, both accurate and speculative, now plays an integral role in how discoveries are perceived by the public. In the case of 3IATLAS, social media has become a double-edged sword. On one hand, it has enabled an unprecedented level of public engagement, with amateur astronomers, science enthusiasts, and curious individuals from all over the world contributing to the growing body of data on this interstellar object. On the other hand, it has amplified misinformation and sensationalism, often overshadowing the careful, methodical approach that scientific inquiry requires. When images of 3IATLAS began circulating online, they quickly went viral. Amateur astrophotographers shared their captures of the object, and within hours these images were analyzed, discussed, and speculated upon in various online communities, from Reddit threads to Twitter conversations. The immediacy of the internet allowed people to draw conclusions before professionals had even had the chance to properly analyze the data. As the object's peculiarities were noticed, its lack of a visible coma, its sharp, almost star-like appearance, social media users eagerly coined terms like alien spacecraft and mystery object, fueling speculation that outpaced scientific analysis.
This phenomenon is not unique to 3IATLAS. It is part of a larger trend in which the rapid pace of online discussion can sometimes lead to premature conclusions. In the case of 3IATLAS, the object's strange appearance and behavior led to an explosion of theories, from the possibility that it was a comet behaving unusually to more outlandish ideas suggesting it was a probe sent by an alien civilization. While public curiosity and engagement are crucial to the advancement of science, helping to bring attention to underreported phenomena, they can also create an environment where conclusions are drawn without the necessary scientific rigor. For scientists working on understanding 3IATLAS, this rapid spread of information presents both challenges and opportunities. On the one hand, the data collected by amateur astronomers and the public's enthusiasm can be valuable contributions to the overall understanding of the object. Amateur observations can provide temporal coverage that professional observatories cannot match, capturing transient events and changes in the object's brightness or behavior. On the other hand, the pressure to release quick results in the face of online speculation can cause scientists to prioritize speed over thoroughness. This tension between scientific rigor and public demand for answers is a complex issue that continues to shape the field of modern astronomy. As more data comes in during the critical December 19th observation window, it will be important for both scientists and the public to resist jumping to conclusions prematurely. The mystery of 3IATLAS demands careful, methodical analysis, free from the pressures of speculation and hype. The involvement of social media has made the scientific process more transparent, but it also highlights the need for accurate, peer-reviewed conclusions. As much as we may want answers quickly, the pursuit of knowledge and science must always prioritize careful observation and critical thinking. When studying objects as distant and dynamic as 3IATLAS, astronomers must contend not only with the complexities of the object itself, but also with the ever-changing conditions of space weather. The Sun's activity has a direct impact on the quality of observations made from Earth. Solar flares, coronal mass ejections, or CMEs, and other solar phenomena can introduce noise into data collected by both radio and optical telescopes. The powerful solar flare that occurred on November 11th and 12th, 2025, serves as a prime example of how space weather can interfere with critical observations. This particular solar flare, classified as an X5.1 event, was one of the strongest of the year. Such flares release vast amounts of electromagnetic radiation across the spectrum, from radio waves to X-rays, and can significantly disrupt communication systems, satellite operations, and radio astronomy.
The intense radiation from this flare flooded the radio spectrum with noise, making it more difficult for radio telescopes, such as the Meerkat Array in South Africa, to detect faint signals from 3IATLAS. Radio observations are crucial for detecting certain types of emissions from comets, such as hydroxyl radicals, which are indicators of water vapor. If 3IATLAS exhibited any significant outgassing during this period, the radio telescopes would have struggled to capture it due to the interference from the flare. In addition to radio interference, space weather can also affect the ionosphere, the layer of Earth's atmosphere that refracts radio waves. When solar flares occur, they ionize the upper atmosphere, creating free electrons that can distort radio signals and degrade the quality of measurements. While optical telescopes are typically unaffected by this, the ionization of the ionosphere can still complicate observations of faint celestial objects by introducing distortion and noise into photometric measurements. This phenomenon underscores the dynamic environment in which astronomers operate. Observing objects like 3IATLAS is not simply a matter of pointing telescopes at the sky. Scientists must also account for the effects of solar weather, which can alter the data they collect. As space weather events become more frequent and more intense due to the Sun's solar cycle, astronomers will need to adapt their observational strategies. This means factoring in the possibility of interference from solar flares and CMEs when scheduling observations of distant objects. For 3IATLAS, the solar flare of November 2025 serves as a reminder that our view of the universe is not as clear-cut as we might hope. The Sun, while providing the light we need to observe, also introduces challenges that can obscure our understanding of objects far beyond our solar system. The rapid advancements in quantum computing are opening up new frontiers in astrophysical research. For decades, simulating the complex dynamics of comets, asteroids, and other small celestial bodies has been a computational challenge. The interactions between gas, dust, and the object's surface, particularly in the case of outgassing comets like 3IATLAS, involve intricate, multidimensional processes that are difficult to model accurately with traditional computers. However, quantum computing promises to revolutionize the way we approach these problems. Helios, a quantum processing unit developed by Continuum, has made strides in modeling complex systems with extraordinary precision. Unlike classical computers, which struggle with the nonlinear and chaotic nature of such systems, quantum computers can simulate these processes in their native form. By harnessing the power of quantum superposition and entanglement, quantum computers can calculate the interactions between particles, the dynamics of gas jets, and the sublimation of ice at an unprecedented level of detail.
For 3IATLAS, this means that scientists could input observational data, such as the behavior of the jets, the object's chemical composition, and the changes in its orbit, and simulate numerous scenarios to test whether the object is behaving like a typical comet or if it is exhibiting truly anomalous features.
Quantum computing doesn't just offer speed, it provides the depth of analysis needed to answer questions that were previously beyond our reach. By simulating the physical processes at play, scientists can test various hypotheses, from the outgassing dynamics to the internal structure of 3IATLAS. This will be essential for understanding the object's behavior and determining whether its features can be explained by known physics or if they suggest something more exotic. The integration of quantum computing into astrophysical research is still in its early stages, but the potential for breakthroughs is immense. As more data is collected on 3IATLAS, the ability to process and analyze this data with quantum simulations will allow for more accurate predictions and deeper insights into the nature of interstellar objects. Artificial intelligence, or AI, is transforming the landscape of scientific research, and its role in the study of interstellar objects like 3IATLAS is becoming increasingly significant. AI-driven models are already revolutionizing fields as diverse as biology, economics, and space exploration. In the realm of astrophysics, AI's ability to process vast amounts of data and identify patterns in complex systems is becoming invaluable, especially when dealing with enigmatic objects like 3IATLAS. In the case of 3IATLAS, astronomers can use AI to analyze the massive datasets generated by telescopes, including light curves, spectral data, and images. AI algorithms can detect subtle anomalies in these datasets, such as unusual patterns in the object's outgassing, jet formation, or orbital acceleration that might otherwise go unnoticed. AI can also model various physical scenarios, testing hypotheses about the object's behavior and its potential origins. By comparing the predictions of these models with the observational data, AI can help refine our understanding of whether 3IATLAS is a strange natural comet, a fragmenting rubble pile, or something else entirely. For example, AI can be used to analyze the shape and orientation of 3IATLAS's jets, track their changes over time, and determine whether their behavior aligns with the expected patterns of outgassing comets. Additionally, AI can assist in simulating different physical models to see if they match the observed acceleration or other unusual behaviors, such as the extreme polarization observed in the object's coma. This ability to quickly process and evaluate multiple competing hypotheses will speed up the scientific discovery process and reduce the risk of human error in interpreting complex data.
Moreover, AI can enhance the precision of long-term observations by identifying key features that need to be monitored, suggesting follow-up observations based on previous data, and even predicting future behaviors of the object. By integrating machine learning algorithms into the workflow, astronomers can make more informed decisions about where to focus their efforts, thus maximizing the scientific yield from limited observation time. While AI is still an emerging tool in astrophysical research, its growing role in the study of interstellar objects like 3IATLAS will likely lead to faster, more accurate analyses of complex data. As the field continues to evolve, AI could become a cornerstone of future space exploration, enabling scientists to tackle questions that were previously thought to be too difficult to answer. One of the most exciting aspects of studying 3IATLAS is the interdisciplinary collaboration it has sparked. This object is not just a subject of interest for astronomers, but for scientists from many different fields, including physics, chemistry, data science, engineering, and even artificial intelligence. The mystery of 3IATLAS requires the combined expertise of researchers with various skill sets, as its behavior challenges the assumptions that have been built into our models of comets and interstellar objects. Astronomers and astrophysicists are, of course, at the forefront of the investigation, using their telescopes and data analysis techniques to track the object's movements, study its jets, and analyze its chemical composition. But physicists, particularly those specializing in fluid dynamics and gas physics, are also crucial to the effort. They can provide insights into how gases behave under the extreme conditions of space and how those behaviors might change when an object like 3IATLAS is subjected to solar radiation.
Chemists are also playing an essential role in studying the composition of 3I-ATLAS, particularly its unusual carbon dioxide to water ratio. By examining the molecular composition of the outgassing material, they can help explain the chemical processes at play and offer potential explanations for the object's extraordinary chemical signature. Furthermore, data scientists and AI specialists are increasingly involved in analyzing the vast amounts of data that are being collected.
The collaboration between these diverse fields not only enhances our ability to study 3I-ATLAS, but also opens up new avenues for future research. As we continue to encounter more interstellar objects, the lessons learned from studying 3I-ATLAS will undoubtedly inform the next generation of space exploration and scientific discovery. The study of 3I-ATLAS is just the beginning of what promises to be an exciting new era of interstellar object research. While 3I-ATLAS is an incredibly rare event, its passage through our solar system has opened up new possibilities for understanding objects from other star systems. The data we collect from this interstellar visitor will undoubtedly have far-reaching implications, not only for our understanding of comets, but for our broader understanding of the universe. One of the most exciting prospects is the future discovery of other interstellar objects. Although 3I-ATLAS is the third confirmed interstellar object to pass through our solar system, astronomers expect that more will follow. With improved observational technologies, including next-generation space telescopes and advanced AI algorithms, scientists will be able to detect interstellar objects earlier in their journeys, allowing for more time to study them. These future objects will likely present new and unexpected challenges, pushing the boundaries of our understanding even further. In addition, the study of 3I-ATLAS could help refine our models of how objects from other star systems interact with our solar system. By tracking the behavior of 3I-ATLAS as it passes through, astronomers can gather critical data on how gravitational forces, solar radiation, and other factors affect the trajectory and behavior of interstellar objects. This data could inform future models of how these objects interact with stars, planets, and other celestial bodies as they travel through the galaxy. Finally, the technological advancements that have been made in studying 3I-ATLAS will likely benefit other areas of astronomy and space exploration. The improved telescopes, better computational models, and more sophisticated data analysis techniques developed for this research will be valuable for studying other astronomical phenomena, from the smallest asteroids to the most distant galaxies. In this way, the study of 3I-ATLAS is not only a milestone in understanding interstellar objects, but a key step in advancing the broader field of astronomy. As we continue to push the boundaries of our knowledge, 3I-ATLAS will undoubtedly remain a cornerstone of interstellar research. The questions it has raised and the mysteries it has presented will continue to inspire astronomers for years to come. And as we move forward, the lessons we've learned from studying this enigmatic object will guide us in our search for more answers, more discoveries, and a deeper understanding of the cosmos.
The study of objects like 3I-ATLAS is not without its challenges, particularly when it comes to the limitations of current observational technology. Despite the incredible advancements in telescopes, both ground-based and space-based, astronomers still face significant hurdles when it comes to accurately observing and tracking distant interstellar objects. The unique characteristics of 3I-ATLAS have highlighted these challenges in new ways, particularly its speed, brightness, and strange behavior, all of which test the capabilities of even the most advanced instruments. One of the primary challenges is the speed at which 3I-ATLAS is traveling. Its hyperbolic trajectory means that it is moving so quickly that traditional tracking methods can struggle to keep up. Most objects within our solar system move along elliptical orbits, which allows astronomers to predict their paths with relative ease. However, interstellar objects like 3I-ATLAS are on a trajectory that takes them in and out of our solar system in a much shorter time frame, making it difficult to track their movement accurately. This means that astronomers have a limited window of time to observe and collect data before the object moves out of range of their telescopes. Another limitation is the brightness of the object. While 3I-ATLAS is bright enough to be detected by telescopes, its small size and compact nature make it difficult to capture in high detail, particularly in amateur observations. The absence of a coma further complicates the situation, as comets typically have a halo of gas and dust that makes them more prominent in the night sky. Without this, 3I-ATLAS appears as a pinpoint of light, similar to a star, making it harder for astronomers to distinguish it from other celestial objects. Even professional observatories struggle to get clear images, and higher-resolution telescopes are necessary to detect even the faintest details. In addition to these challenges, the effects of space weather, as previously mentioned, can have a profound impact on the quality of observations. Solar flares, coronal mass ejections, and other phenomena in the sun's activity can distort or obscure measurements, making it harder to capture clear, reliable data. For instance, radio telescopes are often affected by solar radiation, which can introduce noise into the signals being collected from distant objects. This interference further complicates the already difficult task of studying 3I-ATLAS, as astronomers must account for these disruptions in their data analysis. Given these limitations, it is clear that improvements in technology are necessary to improve our ability to study interstellar objects like 3I-ATLAS. As astronomers continue to develop next-generation telescopes and observatories, advancements in sensitivity, resolution, and data processing will be key to overcoming these challenges.
The ability to observe these objects in greater detail and over a longer period will be crucial in unlocking their secrets and enhancing our understanding of the cosmos. While 3I-ATLAS has captivated the scientific community, it is by no means the last interstellar object to pass through our solar system. Astronomers are already preparing for the next wave of interstellar visitors, and they recognize the need to improve tracking and observation methods to study these objects more effectively. One of the key lessons learned from the study of 3I-ATLAS is the importance of early detection. If astronomers had been able to detect the object sooner, they could have observed it for a longer period, gathering more data and perhaps identifying its unusual features earlier. This highlights the need for more advanced sky surveys that can detect interstellar objects well before they reach our solar system. Programs like the PAN-STARRS, Panoramic Survey Telescope and Rapid Response System, and the Vera-Kerubin Observatory, which are designed to detect moving objects across the sky, are essential for identifying potential interstellar visitors as they approach. In addition to improving early detection, the field of astrometry, the science of measuring the positions and motions of celestial objects, must also advance. Precise measurements of an object's trajectory are crucial for predicting its path through the solar system and for determining whether it will pass near any planets or other celestial bodies. With more accurate astrometric data, astronomers can better plan their observations and track objects like 3I-ATLAS over time, ensuring that no important data is missed as the object moves through our solar system. Furthermore, as the study of interstellar objects continues to evolve, the development of specialized instruments will be essential. Instruments capable of observing objects across multiple wavelengths, such as infrared, radio, and optical, will provide the most comprehensive view of an object's composition, structure, and behavior. These multi-wavelength observations will help astronomers gather more complete data, providing valuable insights into the object's origin, physical properties, and how it interacts with the sun's radiation. As the study of 3I-ATLAS progresses, one of the most fascinating questions that continues to emerge is whether this interstellar object could offer clues to the origins of life in the universe. While it may seem like a stretch to think that a distant object like 3I-ATLAS could have any bearing on the origins of life on Earth, it is precisely this kind of object, one that has traveled through interstellar space for billions of years, that could provide important insights into how life may arise elsewhere in the cosmos.
The key to this question lies in the chemical composition of 3IATLAS.
As mentioned earlier, the object exhibits a high carbon dioxide to water ratio, which is an indication that it may have formed in a much colder environment than our solar system. This suggests that the material making up 3IATLAS could be very old, perhaps even predating the formation of our solar system. If this is the case, studying 3IATLAS could help scientists learn more about the conditions that existed in the early universe and how the building blocks of life might have been distributed across the galaxy. In particular, the carbon dioxide and water present in the object's outgassing could provide clues to the kinds of chemical reactions that might occur on other planets or moons. These chemical processes, which are essential for the formation of life, could have taken place in other star systems and perhaps even elsewhere in the Milky Way galaxy. By studying the composition of 3IATLAS, scientists could gain a better understanding of how life-sustaining molecules form in the depths of space and what conditions are necessary for life to emerge everywhere. In addition to chemical clues, 3IATLAS might also help scientists learn more about the potential for habitability on other planets. The presence of carbon dioxide and other materials in the object's composition could indicate that similar materials are abundant in other parts of the galaxy. If this is true, it suggests that the building blocks of life may be more widespread than previously thought, and that the possibility of finding life elsewhere in the universe is more likely than ever before. The study of 3IATLAS could therefore not only answer questions about the nature of interstellar objects, but also provide valuable insights into one of the most profound questions in science. How did life arise in the universe? And is it possible that life exists beyond Earth? The study of 3IATLAS has not only enriched our understanding of interstellar objects, but it has also catalyzed advancements in space exploration. As astronomers and scientists continue to uncover the mysteries of this unique visitor, it is clear that 3IATLAS will have long-lasting effects on the field of space exploration. The lessons learned from studying this object are setting the stage for a new era of interstellar missions, propelling humanity closer to understanding the cosmos and the potential for life beyond our solar system. One of the key implications of studying objects like 3IATLAS is the need for new technologies designed to reach farther into space than ever before. While our current spacecraft and probes are capable of exploring our solar system, they are not yet equipped to venture beyond the boundaries of our local neighborhood with the same precision. In the coming decades, however, new propulsion systems such as solar sails, ion drives, and even nuclear propulsion will revolutionize our ability to travel to distant parts of the galaxy and potentially visit other interstellar objects.
Solar sails, for example, are an emerging technology that could be used to propel spacecraft using the pressure of light from the sun. This method has already been tested with the successful launch of the Planetary Society's LightSail 2 in 2019. If scaled up and refined, solar sails could provide a propulsion method that allows spacecraft to travel through interstellar space at a fraction of the speed of light. This could enable missions to objects like 3IATLAS, allowing us to get closer to these enigmatic visitors and collect even more data directly from their surfaces. In addition to propulsion advancements, the study of 3IATLAS will likely encourage the development of more advanced observational techniques. In particular, the increasing capabilities of space telescopes, such as the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, will allow scientists to observe distant objects in greater detail. These missions, combined with AI-powered data analysis tools, will enable astronomers to track interstellar objects in real time, potentially giving humanity the ability to detect and study these visitors much earlier in their journeys. Furthermore, the insights gained from 3IATLAS will help shape the development of next-generation space probes. By studying how interstellar objects behave as they pass through our solar system, engineers and mission planners will be able to design probes that are better suited to studying these objects. These probes could be equipped with instruments capable of analyzing the composition, velocity, and physical structure of interstellar visitors, as well as technologies for capturing high-resolution images from a variety of angles and wavelengths. With these advancements, humanity will be better equipped than ever before to explore the universe beyond our solar system, pushing the boundaries of what we can learn and discover about the cosmos. The study of 3IATLAS has shown that the exploration of interstellar objects is a global endeavor that requires collaboration across borders, disciplines, and technologies. The unprecedented nature of this interstellar visitor has brought together astronomers, physicists, chemists, engineers, and data scientists from all over the world, working together to unravel its mysteries. This international cooperation has been instrumental in gathering the data needed to understand 3I-ATLAS, and it highlights the importance of collaboration in the future of space research. The involvement of various space agencies and observatories has made it possible to gather a wide range of data from different perspectives. For example, NASA's Hubble Space Telescope and ESA's Gaia mission have provided critical observations of the object, while the European Southern Observatory, ESO, in Chile, has offered ground-based observations with its Very Large Telescope, VLT.
Similarly, amateur astronomers around the world have contributed their own observations, adding valuable insights and broadening the scope of the research. As we look to the future, the role of international partnerships in space exploration will only continue to grow. In order to study interstellar objects more comprehensively and to plan future missions to distant regions of the galaxy, countries and organizations will need to collaborate on a scale never before seen in the history of space exploration. The scientific community has already recognized the benefits of such collaboration. Combining resources, expertise, and data from around the world has led to more accurate and complete findings than any single organization could achieve on its own. In particular, international partnerships will be key to the success of future missions to interstellar objects. Launching spacecraft to the outer reaches of the solar system and beyond requires significant resources, both in terms of funding and technology. By pooling resources and expertise, countries can share the costs and risks associated with these ambitious missions. For example, the collaboration between NASA, ESA, and other space agencies has already proven successful in numerous missions, including the recent launch of the James Webb Space Telescope. Similar collaborations will be essential for future interstellar missions, ensuring that humanity is well prepared to study these fascinating visitors from other star systems. Furthermore, the study of 3I-ATLAS and other interstellar objects could serve as a catalyst for broader scientific and technological collaborations. By working together to solve the mysteries of the universe, researchers and institutions can make strides in fields such as space propulsion, AI, quantum computing, and materials science. These advancements will not only benefit space exploration, but will also have far-reaching implications for a wide range of industries here on Earth. The discovery of 3I-ATLAS and its passage through our solar system has captured the imagination of people around the world. It is not just a scientific breakthrough, it is a cultural event that has inspired awe, wonder, and speculation. The idea that we are not alone in the universe, that there are objects from other star systems, potentially with very different properties than anything we have encountered in our own solar system, has profound implications for how we view our place in the cosmos. For centuries, humanity has gazed at the stars and wondered about the possibility of life beyond Earth. The study of interstellar objects like 3I-ATLAS brings us one step closer to answering that age-old question. While we have not yet found evidence of life on 3I-ATLAS or any other interstellar object, the mere fact that these objects exist forces us to reconsider our understanding of the universe. What are the chances that other forms of life might have evolved in distant star systems?
Could these objects carry the building blocks of life, or even evidence of ancient civilizations? The discovery of interstellar objects also raises philosophical questions about the nature of the universe itself. Are these objects simply the remnants of long-dead stars, or do they represent something more? The possibility that 3IATLAS could be an artificial object, a relic from an advanced alien civilization, adds another layer of intrigue to the mystery. It challenges our assumptions about the uniqueness of our solar system and raises the possibility that intelligent life may be more common than we think. In addition, the study of 3IATLAS has sparked renewed interest in space exploration, with many seeing it as a symbol of humanity's potential to explore the far reaches of the galaxy. As we learn more about this object and others like it, we are reminded of the vastness of the universe and our place within it. The pursuit of knowledge about 3IATLAS and other interstellar objects may one day help us answer fundamental questions about the origin of life, the nature of intelligence, and the future of humanity in the cosmos. While 3IATLAS is primarily being studied for its interstellar origin, its passage through our solar system offers valuable insight into the broader evolutionary history of our solar system. Objects like 3IATLAS, which travel through space from other star systems, provide a snapshot of the conditions that existed long before our solar system formed, and can offer clues to the early stages of planetary formation in distant regions. The fact that 3IATLAS appears to be composed of ancient material, its high carbon dioxide to water ratio suggests it formed under colder conditions, could also provide new insights into the chemical makeup of the early solar nebula from which our solar system was born. Understanding the composition and behavior of interstellar objects like 3IATLAS could help astronomers refine their models of how solar systems form and evolve over time. By comparing the characteristics of interstellar objects with those of objects in our own solar system, scientists can gain a better understanding of the material that makes up planetary systems. For example, many comets in our solar system are believed to be remnants from the outer reaches of the solar system, left over from the formation of the planets. Similarly, interstellar objects like 3IATLAS may be the remnants of processes occurring in other star systems, providing a glimpse into how planets and other celestial bodies form in different environments. The passage of interstellar objects through our solar system is a rare event, but it holds immense scientific value.
By studying 3IATLAS and other interstellar visitors, scientists can gain valuable data on the composition, dynamics, and origins of these objects, and use that knowledge to improve our understanding of the early history of our solar system and the broader galactic environment in which it resides. The passage of 3IATLAS through our solar system has already changed the way astronomers approach the monitoring of the skies. As a result of this object's unexpected characteristics and the attention it has garnered, there is now a renewed focus on the need for better detection and tracking systems for interstellar objects. While 3IATLAS was detected relatively early in its journey, future objects may not be so easily identified, especially if they are faint or if they approach the solar system from a direction that is not well observed. One of the primary challenges in detecting interstellar objects is their speed. Because these objects are not gravitationally bound to our solar system, they can travel through it at extremely high speeds, often much faster than objects that are orbiting the Sun. This means that interstellar objects may only be visible for a brief period, making early detection crucial for gathering as much data as possible. The longer the object is observed, the more opportunities astronomers have to study its behavior and to track any changes in its trajectory or composition. To address this challenge, astronomers are calling for more robust sky surveys and improved detection systems. Existing programs like Pan-STARRS and the Vera C. Rubin Observatory have already made significant strides in detecting small objects in the solar system, but they are not specifically designed to spot interstellar visitors. The addition of dedicated interstellar object tracking systems could significantly improve our ability to detect these objects early in their journey and collect more data before they leave the solar system. In addition to better detection systems, astronomers are also working on developing methods to track the trajectories of interstellar objects with greater precision.
Current astrometric data is often limited in its accuracy, especially for objects that are moving quickly through space. By developing more advanced tracking systems, astronomers can better predict the paths of interstellar objects and ensure that observation efforts are focused on the most important targets. As the study of interstellar objects becomes a more prominent field of research, the development of new technologies and systems will be essential for ensuring that we can detect, track, and study these mysterious visitors with greater efficiency. 3IATLAS may be the first of many interstellar objects to pass through our solar system, and by improving our ability to monitor the skies, we can ensure that we are prepared for the next wave of discoveries.
While 3IATLAS is not believed to contain life, its passage through our solar system has reignited questions about the potential for life beyond Earth. One of the most profound implications of studying interstellar objects like 3IATLAS is the possibility that they could carry the building blocks of life, or even evidence of life itself. Although there is no direct evidence that 3IATLAS contains any form of life, the discovery of complex organic molecules in interstellar space and the study of material from other star systems have reignited interest in the field of astrobiology. Astrobiology is the study of the potential for life beyond Earth, and it encompasses a wide range of scientific disciplines, from chemistry and physics to astronomy and planetary science. The study of interstellar objects like 3IATLAS could help astrobiologists understand how life might arise on other planets or moons, and whether the ingredients necessary for life are widespread throughout the galaxy. If the chemical composition of 3IATLAS contains complex organic molecules, it could suggest that the raw materials for life are more abundant in the universe than previously thought. The presence of water, carbon dioxide, and other volatile compounds in 3IATLAS's outgassing suggests that the object may have been formed in an environment where these ingredients were present and that they have persisted throughout the object's journey through space. This raises the intriguing possibility that similar objects and other star systems could harbor the building blocks of life. In addition to studying the chemical composition of interstellar objects, scientists are also exploring the possibility that these objects could be carriers of microscopic life forms. Some researchers hypothesize that life may not only form on planets, but could also travel through space on objects like asteroids and comets. Known as panspermia, this theory suggests that life could be distributed throughout the galaxy via the movement of space debris. While the idea of life being transported across vast distances remains speculative, the study of interstellar objects like 3IATLAS offers a unique opportunity to test this hypothesis and explore the potential for life beyond our solar system. The passage of 3IATLAS through our solar system has had a significant impact on how science is communicated to the public. Unlike most astronomical discoveries, 3IATLAS has captured the imagination of a global audience, generating widespread public interest.
The speed with which information about the object has spread across social media platforms has sparked an unprecedented level of engagement, creating an opportunity for scientists to interact with the public and share their discoveries in real time. This shift in science communication is particularly evident on platforms like Twitter, Reddit, and YouTube, where amateur astronomers, science enthusiasts, and curious members of the public have engaged in lively discussions about the object's mysterious nature. Social media has allowed the public to follow the progress of the object's observations, ask questions, and even contribute their own observations and interpretations of the data. This level of public engagement, combined with the transparency of modern scientific processes, has given rise to a new model of science communication, where the boundaries between professional researchers and the public are increasingly blurred. For scientists working on the study of 3IATLAS, this change in how science is shared with the public has both advantages and challenges. On one hand, the increased accessibility of scientific data has fostered a sense of collaboration and inclusivity, as amateur astronomers and citizen scientists have contributed valuable data and observations. These contributions have enriched the overall body of knowledge and provided fresh perspectives that might have been overlooked in more traditional, isolated research environments. On the other hand, the rapid spread of information also has its drawbacks. The speed at which data is disseminated on social media platforms can lead to the spread of misinformation or premature conclusions. In the case of 3IATLAS, there have been numerous claims, some speculative and unfounded, about the object's true nature. The idea that the object could be an alien spacecraft, for example, spread quickly across social media despite the absence of any concrete evidence. Such speculation, while exciting, can divert attention from the scientific process and create confusion about the object's true nature. Scientists must carefully navigate this environment, balancing transparency with the need for thorough, methodical analysis. Ultimately, the case of 3IATLAS highlights the growing importance of science communication. As we continue to make discoveries about the universe, it is crucial that scientists engage with the public, share their findings openly, and clarify any misconceptions. The ability to communicate complex scientific ideas in an accessible and understandable way is becoming more important than ever before, especially as the public's interest in space exploration and astronomy continues to grow. As we continue to study interstellar objects like 3IATLAS, it's important to consider the ethical implications of these discoveries.
While the study of distant celestial bodies can offer valuable insights into the origins of the universe and the potential for life beyond Earth, it also raises important questions about how we interact with these objects and whether we should consider their potential impact on our own planet. One of the most pressing ethical questions involves the potential for contamination. If we were to send a spacecraft to study 3IATLAS up close, would it be possible to ensure that no contamination from Earth's biosphere would interfere with the object's pristine nature? Scientists have long considered the risks of biological contamination when studying comets, asteroids, and other small celestial bodies. In the case of an interstellar object like 3IATLAS, the risks are even greater. The object may have been traveling through space for billions of years, and its composition could hold clues to the early conditions of the universe. Any introduction of Earth-based life forms could compromise the integrity of the study and erase valuable information about the object's origins. In addition to contamination concerns, there are also ethical considerations regarding the study of potential life. If future interstellar objects are found to contain microbial life or the building blocks of life, scientists will face difficult questions about how to handle these discoveries. Should we attempt to communicate with or study extraterrestrial life forms, or should we take a more cautious approach, preserving the natural state of these objects? The discovery of life beyond Earth, even in its most basic form, could have profound implications for our understanding of biology, ethics, and our place in the universe. The ethical considerations surrounding the study of 3IATLAS and other interstellar objects underscore the need for a responsible, transparent approach to space exploration. As we continue to push the boundaries of science and technology, it is crucial that we consider the broader implications of our discoveries and ensure that we are making decisions that are ethically sound and scientifically rigorous. While 3IATLAS is still at the forefront of the scientific community's attention, astronomers are already looking ahead to future interstellar visitors. The passage of 3IATLAS has shown us that interstellar objects are not as rare as we once thought. As detection technology improves, astronomers expect that more objects from outside our solar system will be detected in the coming years. Some of these objects will likely be similar to 3IATLAS, while others may present entirely new challenges and opportunities for scientific discovery. One of the key areas of interest in the study of future interstellar objects is their potential for providing information about the interstellar medium, the vast empty space between stars. Objects like 3IATLAS carry with them material that has been exposed to cosmic radiation and other forces over billions of years.
By studying these objects, scientists can gain valuable insights into the conditions of the interstellar medium, which is not easily accessible by other means. The more we learn about the interstellar medium, the better we can understand the processes that govern star formation, planetary development, and the distribution of matter in the galaxy. Another exciting prospect for future interstellar objects is the possibility of discovering signs of extraterrestrial life. While 3IATLAS does not appear to contain life, future interstellar visitors could offer clues to the existence of life in other star systems. The discovery of organic molecules, complex chemistry, or even microbial life on interstellar objects would be one of the most profound breakthroughs in the history of science. Such discoveries could reshape our understanding of biology, evolution, and the potential for life beyond Earth. As technology continues to advance and our ability to detect and study interstellar objects improves, the future of interstellar exploration looks incredibly promising. With each new object we discover and study, we will continue to expand our knowledge of the cosmos, unlocking new mysteries and deepening our understanding of the universe. The study of interstellar objects like 3IATLAS provides astronomers with an extraordinary opportunity to explore the cosmic origins of our solar system. As we learn more about the physical properties and composition of objects that have traveled through space from other star systems, we are not only unraveling the mysteries of the objects themselves, but also uncovering the broader processes that govern the formation of stars and planets in the galaxy. The passage of 3IATLAS through our solar system has opened a window into the composition of material that has been traveling through space for billions of years. The object's high carbon dioxide to water ratio, along with other peculiarities in its chemical signature, suggest that it may have formed under conditions very different from those in our solar system. This provides an opportunity to study the processes that occurred in other star systems, and it may reveal critical information about the conditions that existed in the early universe. Objects like 3IATLAS are relics of the interstellar medium, the vast cold expanse between stars that is often invisible to our current observational methods. The material carried by such objects provides a snapshot of the primordial building blocks of the universe. By studying these interstellar visitors, we can gain insights into the types of molecules, gases, and dust particles that were present during the early formation of stars and planetary systems, helping us understand the broader evolution of matter across the galaxy. Furthermore, the study of interstellar objects challenges our assumptions about the uniformity of the universe.
While many objects in our solar system share similar characteristics, interstellar objects like 3IATLAS reveal that other star systems may host entirely different types of material, chemistry, and physical structures. This diversity provides a glimpse into the myriad possibilities for star and planetary formation, suggesting that the universe may contain far more variety and complexity than we have previously imagined. In the future, the study of interstellar objects will likely become a cornerstone of astrophysical research. With more advanced observational tools and a growing understanding of the dynamics of these objects, we can expect to gain deeper insights into the forces that shape the formation and evolution of the universe. The lessons learned from studying 3IATLAS will guide future research, helping scientists refine their models of how stars, planets, and galaxies form. As the study of interstellar objects becomes more important, the need for international collaboration in space exploration has never been clearer. The complexities involved in studying these objects, as well as the scale of the technological and financial investment required for future interstellar missions, make it imperative for countries and organizations around the world to work together. The collaboration between space agencies like NASA and ESA and other international partners has already proven essential in the study of objects like 3IATLAS. These collaborations allow for the pooling of resources, expertise, and technology, enabling scientists to gather data from a wide range of instruments and observatories. With the global nature of space exploration, countries with different scientific and technological strengths can contribute to the discovery and analysis of interstellar objects. Future missions to study interstellar objects up close, whether through robotic probes, sample return missions, or other innovative approaches, will require unprecedented levels of cooperation.
The challenges of designing spacecraft capable of reaching and studying objects traveling at high velocities are immense. By pooling the expertise and resources of multiple countries, we can ensure that these missions are not only successful, but also cost-effective. The growing field of interstellar research is also benefiting from cross-disciplinary collaboration. As the study of these objects involves multiple areas of science, such as chemistry, physics, astronomy, and engineering, scientists from various fields are working together to develop new methods of observing and understanding interstellar visitors. The synergy between different disciplines has already led to breakthroughs in our understanding of interstellar objects, and as research progresses, this collaborative approach will continue to be essential.
Moreover, international cooperation in space exploration will not only advance our knowledge of interstellar objects, but will also strengthen diplomatic ties and foster peaceful collaboration in the pursuit of scientific discovery. As more nations participate in space missions, the global nature of space exploration will become an even greater asset, facilitating cooperation on a range of scientific, technological, and political issues. The discovery of 3IATLAS and its peculiar characteristics has ignited widespread speculation about the possibility of extraterrestrial life. While there is no evidence to suggest that the object harbors life, the fact that it comes from another star system raises intriguing questions about the potential for life in other parts of the universe. The study of 3IATLAS serves as a reminder that life may exist in forms we have not yet imagined, and that the search for extraterrestrial life is a more complex and multifaceted endeavor than we once thought.
Ultimately, the study of 3IATLAS and other interstellar objects will continue to shape our understanding of the universe, offering new perspectives on life beyond Earth and the potential for intelligent civilizations in other parts of the galaxy. By exploring these objects, we are not only learning about the past and future of our own solar system, but also investigating the broader questions of life and existence in the cosmos.